40 years ago, the new areas of study called chaos and complexity science intrigued scientists with ideas like the butterfly effect and systems that can organize themselves. However, the type of math needed to fully understand these ideas is still not well developed. Even though physics uses complex math, it has not yet solved the tricky, nonlinear equations that are key to explaining the most fascinating natural behaviors. Trying to solve these equations has been more like making smart guesses than doing exact science. This problem is clear when we try to use computers to model complex systems, like predicting the weather. Computers have to use rough estimates and generalizations, and sometimes they get tripped up by the small things they miss, like how a butterfly fluttering its wings might affect the weather far away. To get a better grip on the complex web of nonlinear interactions, we need a deeper understanding of the physical laws that create and control complexity. The term edge of chaos is used to refer to a phase transition space between order and disorder that is hypothesized to exist within a wide variety of systems. This transition zone, known as the edge of chaos, is a region of bounded stability that creates a constant dynamic interplay between order and disorder. This point or interface between the two is hypothesized to be a locus of maximum complexity and the driving force of evolution within many types of systems. It's thought that the human brain works in a similar state of fine balance, perhaps tinkering at the edge of chaos. Physicist per Bach's theory, which sees natural systems as naturally leaning towards this critical balance, like when sandpiles form and then collapse, suggests that our brains might be self-organizing to use this balance. Tests with rat brain cells have shown activity patterns that look like this critical balance, which could mean that our brains are working best when they stay near this edge. These complex patterns in the brain cell activity might help with efficient memory storage, passing signals, and quick responses. There's still a lot of debate about how important this critical balance is for thinking and health, with some critics thinking the patterns seen are just random. Even so, this theory's possible help in understanding brain activity and influencing computer design keeps researchers interested. Whether the brain works exactly at this critical point, or uses ways to correct itself to stay close to it, getting to know this balancing act could teach us a lot about the mysterious ways the brain works. Stay tuned for episode 5, where we will take a closer look at the emergence of life.